So, first thing, what you remember about capacitance? Capacitance is what? The charge stored per unit voltage. And we know that the SI unit is farads, right? Remember, it's generally something else small, right? How else we could find capacitance? Remember, permittivity of free space by the area all over the distance. Anything missing? That's it? Yeah? Right? We also talked about the ability of a capacitor to charge and discharge, right? Remember capacitor? Two parallel plates separated by a distance t, right? And we said that the area is here and the permittivity of the material inside here, right? Right? Something else that we need to remember. We need to remember that the capacitor has the ability to store charge and discharge as well, right? So during charging, and I explained the process, right? During charging, we should remember what the I, Q, and V graphs look like. And then during discharging, this one easier to remember, what the I, Q, and V graphs look like. What's the I graph here? I not equal to? I not equal to what? Sorry, I is equal to I naught by what? E to the minus so on RC. Right? And all these here are the same thing, right? Write them down. Oh, no, not yet. Ready? So, well, I can add this writing the formula somewhere in the meantime. Huh? Well, I can just write it in well. I mean, like writing it in your book. Not this one here. Right. This one here will be the same thing minus tau and RC. This one here will be Q naught E minus tau and RC. This is V naught E minus tau and RC. What do we call RC again? We call tau the time constant, right? And it has the same SI unit as RC. And how does this formula change? Q naught by what? 1 minus, right? So the questions today will incorporate everything that we're going to do, right? And V is equal to V naught I minus E tau on RC. Right. And I also gave you the energy stored. Energy stored is what? A half what? I find energy stored by capacitor. Huh? A half CV squared or a half V cubed. Right? That's energy stored by capacitor. Right. Now, what happens when we take the capacitor and connect them in series and parallel? Right? So I want you to try to prove it from a trying to look back. I'm going to give you an example using the resistor. And I want to see if you could find the formula for capacitance. Right? Capacitance in parallel. Let's do the easy one first. And then series. Right? So if I connect three capacitors like this. That energy stored by the capacitor. Right? Remember, you have to be able to explain this as well, right? Remember how I explained this to you last week. You have to be able to explain how it stores charge and how it discharges, right? So let's say I gave you three capacitors. I want you to try to prove the formula. This is C1, this is C2, this is C3. Right? So I want you to try to prove this. How are you going to prove that, right? Right? And I'll give you a startup. Whenever something in parallel, what do we know constant? If I give you a circuit and I tell you in this circuit, one of these variables constant, which one it is? Huh? Voltage. Voltage in parallel is the same, right? So, and what splits up? What splits up? Current, right? And we know that current and charge kind of inversely related. Yeah. So if I have charge coming in here and it's Q, then that charge will split up here, Q1. It will split up here, Q2, and split up here, Q3. Huh? So the charge will split up, just like a current. Current and charge, they directly related, right? So the total charge in this circuit here will be Q1 plus Q2 plus Q3. What we had to do now is to find a way to bring in capacitance, right? Yeah. So what do we know about charge? We know that Q is equal to what? Q is equal to CV. So Q is equal to the total charge by the voltage. What is Q1? Q1 is the C1 multiplied by same V or same V. Why? Because voltage is constant. And here will be what? C2 by V, and here will be C2 by V. No, what you can do is divide by V, because they all have V's in them, right? Yeah. So you can divide by V. Sorry. Yeah. Oh, very good. Very good. So now we end up with something like this, right? We end up with C is C1 plus C2 plus C3. So this is the formula for capacitance in parallel, which is the same as resistance in series. So you have to remember capacitance and resistance, the formulas inversely, right? Inverted. Okay? So what I want you to do is draw a diagram with series and see if you can prove it. All right? And then we're going to apply all of this. Right? Please remember this, those who forgot these rules, current and voltage, series, parallel. Current in series is the same. Here it splits up. Here is splits up. Here is the same. Again, without looking at the answer. Close to it. Right, and then you get it right out. What is B? Same sequence. Like that's it. Right, and now right was B. So you can do it the same way. It's the gotta work it out. Right, you're doing it the same way, right? You put three capacitance in series, C1, C2, C3. And if you find the voltage here, the voltage here, and the voltage here, you would recognize that V is equal to V1 plus V2 plus V3. And of course, we're going to replace V, right? If we rearrange that formula there, V is Q1C. So it's Q1C1 plus Q1C2 plus Q1C3, right? And the reason we leave Q the same is that the current is the same or the charge is the same for each one. All right. And if we rearrange and we divide by Q now, right, we divide everything by Q, we end up with this. 1 on C is 1 on C1 plus. Right, so combine everything here. These are the things that we need to know about capacitance. All right, so we're going to try some easy and then some hard ones, right? But please remember, right, you have to use these rules. Right, so what I could do here for you, Actilia, is to add in some more things here for you. Right, in series is 1 on C is equal to this. And in parallel is, right? So this is the table I have to learn. Everything here is what you need to know about capacitance. Okay? There's a graph that I wanted to do about. Right? There's a graphical one that we need to do. How do you linearize things like this, Olia? Match people. Log. Right? You take log on both sides and work it out. Right? So I'm going to show you one of these, right? How to linearize them and like find for these values. What do you reckon? So we're gonna try one here, right? quick thing there. What I think here, it's a multiple choice. I like to start with a multiple choice, right? What's the capacitance there? Which statement is correct? Exact. Right. Enough? On that shit on. Oh. Alright, are you ready? We all think A, B, C, or D. Huh? So those two are in parallel, so for sure it's not the parallel formula, right? Now the charges on the capacitors are equal. Can you tell that? Right? The energy stored by the two capacitors is the same. And the potential difference across it is the same. Huh? What did we learn? What did we learn about voltage in parallel? It's the same. So what's the answer? Dog. The answer is dog. Right? The potential difference across each is the same. Have we learned that here? Dog, yeah. Have one more thing. Alright. This one kind of easy, but what's the answer? What's the answer for this one? 100 microfarads, right? And they give you the voltage. What's the energy stored? They give you capacitance and voltage, yeah? Please remember you have micro there. How you doing yours? Finish it. Yeah, next. You have one? Micro. I will do it. Yeah. What you all got? Work it out, please. Excuse me, Celia, I can work it out, please. What's the formula we're going to use? Huh? I have CV squared, right? I have CV squared. How much you got? Four. Yeah, I got four.
Yeah, I got four. I got four. I think it's.
I mean, I got four, work it out. It's a half, oh, sorry, it's a half, so two.
Right, yeah.
Two, right?
Two, yeah.
Two. All right, nice. All right, now let's go to the actual calculation here. They asked it to derive part A and B, but you're not gonna do that, right? So let's focus on here. Copy it up. Right? Before we move on, the first 3 and the 9, they are in what? The 3 and the 9. The 3 no, the 3 and the 9. Parallel, the 10 and the 14. Right. If you turn them into 1, those two are in what will over the 8?
Series.
Right?
Yeah.
Right. Yeah, turn into 1, then apply the series formula, right? Just like Form 5, we did some questions. Alright? Go ahead. Do part C, please. Actually work it out. Hurry up, try that fast, please. Find the total of capacitance and let's work it out. Try all the parts and then I'll start to work it out, right? Right, so done. Okay, do the first part, or you looking so? Oh, yeah, show it up quick. Right, and then you work it out. Please remember your values are in micro. Please remember it in micro. Right, I got 12 here. And 24 here. Right, remember those in parallel, so I use the parallel formula, right? And then part one, you have to find the total. That's 1 on C. Right, it's okay if you use everything in micro, your answer will be in micro, right? No.
Oh.
Alright, you're done? Right, so that's 1 on 12. 1 on 12 plus 1 on 8.
Plus 1 on 20.
1 on 20.
There's no quarter.
When you add a quarter,
Yes. So
that means C is 4 microfarads, right?
mostly.
But that's not what the question asks. But it shows 12, right? But it shows a quarter, right?
Yeah.
Right, but That's not what they asked for.
What else?
Oh yeah, sorry, I was wrong. Part 2, they asked for total charge.
Yeah, I guess that was question.
Right? Total charge. How you finding total charge? C by V, nice. 4 by 10 to the minus 6 by, so I got 24 microcoulombs. Yeah? Go ahead. So part 1 and 2 good. Part 3 is what I want to see. Apply this stuff now. Part 3. They want the charge stored by the eights. So they want the charge stored by this one here. And what's the PDF cross it?
Yeah.
Well done? Right, question. What will be the charge stored on the 8 Joshua? What will be the charge stored by the 8 microfarad capacitor? Well, you know about voltage, sorry, charge in series is what? We just learned that here. Charge in series is what? So does it vary or is it the same?
In series.
Yeah.
In series.
Same. So what will be the charge on the 8 microfarad capacitor? If the total charge is 24 and remaining the same, 24, right? So the charge will also be 24 microcoulombs, right? But what would the voltage be, Nathaniel?
So it's there.
Yeah,
Yeah, see the value of the just
right? And how you find voltage?
right.
Well, we could use that relationship there, right? Q1C,
Yeah.
right? So that's 24 over 8. I got 3 volts. 3 volts. Right? Where? What is micro cancel? What is micro cancel? Susanna, you okay with that? Right, move on. Try the rest. So as I said, you have to use that little table on the top there, right? Go ahead. Try part 1.5.
You got outside, right?
No, I don't like Big Friday and Saturday. See, I don't really like that. Cannibal Friday.
So you get something else.
And if I do it online, all the would come.
Yeah, so wait.
Huh? Nothing. No, I don't want to have class here. And if I have class online, all the would come. So I just start double up. Yeah, we're going, but I'm not sure it's Friday or something.
So that's what I'm asking.
I think it's going to be.
So the answer is 24 jobs.
I don't know, that's how you see.
Yeah.
Oh, I was yeah.
Yeah, so you got it.
Huh?
You got it.
Yes, you are. That one.
It's not it.
Oh yeah. It's still on part 3. I was done. That wasn't right. Are you done?
Yeah.
Are you done?
Yeah, so
Right, so find the charge in the 10, right? We have a slight problem now. I'm just going to erase it a little bit, right? We have a slight problem here. What happens in parallel? Right? What will happen here is that the charge will split up here and here. Right? The charge will split up there and there. Okay? So yeah, you have two options. We know how to find charge, right? Charge is what? Right? We know that Q from our formula there is capacitance by voltage. We know the capacitance is 10, but we don't know the voltage. How we get any voltage? That's one way you can do it. But watch this here. And we found the voltage here was 3 volts.
yeah.
Can we do the same? How would I treat them?
No, that's not true.
DC parallel together is three. Start group.
Yeah.
I mean the two parallel.
Yeah.
Oh yeah, but I don't have to something.
So 24, but I don't know.
What was this total value again? 24?
Yeah.
Right. So all we have to do is the same thing again to find the voltage.
Right.
Right? What was it again? So the voltage across those two was 24. Sorry. Yeah, 24. We're using this formula here, Q and C. Right? Right? The total capacitance is 24 micro and the total charge is 24. So when I divide them again, 1 volt. So here is 1 volt and here 2 volts. That's okay? Benson? Sure. So now Q is equal to what?
CV.
Right? CV. And the C is 10. Here you have to use 10 to the minus 6. Multiply by 1 volt. Right? So your final answer there is 10 micro. 10 microcoulombs. And how much underneath? Was the charge stored in the 14 microfarad? The top is 10, so the bottom is what? 14, right? Because it has to add back up to 20.
Yeah.
Yeah,
It's never going to show you.
I know.
Yo, the dog sitting on.
Yeah. Right, so that's part 2, 3, 4, 5 now. 5 now. How we find the total energy, Atelier? What we using for total energy? Nice. 271, so without complaining. Right, W is equal to a half VQ. Yep. V is 6. And the curve, and Q is what?
I don't know.
And Q is 24 microfarads, right? Sorry, microcoulombs. Right, so that's 3 by 24. Right, that's around what? 72?
Yeah.
72 microjoules. Yeah. 72 microjoules. Everybody clear it up? Right, you want to go a little bit harder now. Right, there's one that we had to a graphical part, but all the number and so oh, you gotta draw the graph, thanks. I remember that.
Basically, graph is all about it. What? So,
I'm gonna give it a person. Everybody writes it? Oh wait, I had one more multiple choice. Which one is the highest? Which one is the highest? Which one? A, B, C, or D? A, B, C, or D? You don't need values to work without. Dog? Yeah. The one where all in parallel, right? The one where all is in parallel. Right. What is graph here? Right, so I need a little table, right? Look at the formula here. Here we have some discharging, right? So we have the same formula I have on the board. V is equal to V naught E to the minus T on RC. But look at the graph that it drew. Right? Okay, negative gradient, but look at the y axis that take up. What did plus on the y axis? What did plus on the y? No, ln V. No. See the ln? So what do we do to obtain this graph? We have to what? Linearize, right? Do my favor now, take ln on both sides and linearize somehow. Take ln on both sides and linearize. That's what I was talking about earlier, right? They punch you, linearize thing from now.
I don't know if you're. So be it. I was when I looked at the. That's Ian something. So what's next?
Huh?
What's next?
Well, sir, I never did.
EXP is E.
Yeah, going to the linearizing just now.
X.
Oh, EXP is like E.
Yeah.
So instead of writing E, they write CX. Just now I'm finished. I'm gonna linearize just now. I just give that to you. Sometimes I have to apply line on both sides. To the so that's yeah, some get the linearize.
Well, I'm not sure. So,
Yeah.
they have asked that, well, what the proof we have C squared, you have EQ. That they have asked that. Right, so if you.
See.
Or you get to the linearization.
Yeah.
When you linearize, put it in the form y is mx plus c2. I'm gonna do it just now.
Yes.
I'm gonna do it just now, right? But and in your answer, write down what is the gradient and what is the y-intercept. Finish already and yeah, do that. You do this in module 3, unit 1. Same example. Huh? Do what again? Huh? What? Don't we do that? Hold this, don't bump. All right, so watch here. If I take ln on both sides, let's zoom in here to do it, right? You'll end up with ln v is equal to ln v naught e minus t on rc. This is multiplied. So in ln, whenever you multiply, what you do? Right? So you see if I have a multiplied between here, you split it up and you write it like this. You write it like this: ln v naught plus ln e to the minus t rc. Right? And then you can take the power and put it in front. Right? That's a rule for ln, right? So you'll end up with ln v is ln v naught minus t on rc ln e. So after the power, I put it in front, right? And we know ln e is what? Ln e is 1. So if I rearrange this, I will end up with minus 1 on rc multiplied by t plus ln v naught. Right? If I just rearrange it, because ln e, that value there is 1. Ln e is 1. Right? So this will be a y-axis. That's what the graph plots. This part in bracket here is the gradient. This part here is the x. Remember the graph? What was the graph? Ln v versus t, right? So the x-axis has t, and ln v naught is here, c. All right? That's the way you linearize. Anyone you can do it like that. Q, V, anyone. I. Yeah. What? What? After this question, if you think.
I got top now. They said you want my shop. I'm going to
Now you've got more. answer for, yeah, so you just have to learn top here. But now see, do I have to go back and learn all you? Yeah, any question in this form, you can do it like that. Right, now we're going back to the graph to find a few things, right? What does the grade of the graph give you? Minus 1 on RC, and the y-intercept gives you ln V naught, right? So you can work backwards and find V naught if you need it. Copy it down and let's go to the graph. After this, I'll give you a small break, right? It's still half 8, huh?
What?
What time class is half 8 or 9?
It's eight.
Have you start half past?
Yeah, it's not how bad.
If you want to get the extra parts, it's pretty same price.
Yeah, exactly. So you can just go it up and.
No, you should have even that.
Yeah, I didn't know. I didn't.
Well, no.
Yeah, I can. You can stop eating because I'm hungry.
That's all. That's all.
It is say after school.
So, yeah, well, breakfast, that.
After school, you can play.
Well, breakfast, that.
Oh, it's a play to school, yeah.
Right, so I was having go for so.
And I want something right there. And I take it.
Yeah, but the normal.
All right, let's go now. So calculate the gradient and hence find the time constant. Time constant is what? RC, right? I write this bad. It should really be T. Fix these to T, right? Not tau. Tau is RC. Right? Just fix that for me. I write this bar. Right? There should be T. And RC is tau. Right? So tau is RC. Sorry about that. All these should be T. Yeah, no, normal T is normal T, but RC is the tau. Right?
I literally said it, yeah, I literally said it.
Yeah, somebody did say that last week, yeah? Yeah, all it's no normal T. All is normal T, but RC is the tau. Go ahead now. Find the gradient, please, and let's find RC.
Listen, you know, also about the last week, when you're ready ground straight.
Well, let's see. I put tau by mistake, sorry. Yeah, sorry. I think I didn't write tau as RC last week.
Oh, singing this school, I think, so.
We have to do that.
It's not practice.
We'll probably take it out because of how you play to class on. Right, teacher.
See you.
We have to take on the board.
See
Yeah, we'll get the gradient. Please look at the values at the bottom as negative, huh? Right? That's negative. Oh yeah, find right over run and think of what to do. Pick two values. What's the value on top about 2.2? It's looking like about 2.2.
I'm not worried. They got who was you.
This is minus 0.3.
And
Right, so you can use rise and run 2.2. This is 2.5. And the width is 50. Right, so for my gradient, I got 2.5150. Right? I get what? 0.05. Yes? 0.05. And what else gradient equal to? Minus 1 on R. Oh, by the way, gradient is minus, minus. So it means that RC is equal to 1 over 0.05. Right? How much is that? 20? Work it out. So that's 20. What's the unit? Second. 20 seconds. What's the definition for RC again?
Resistivity by capacitance.
Definition. Time taken to reach what?
Um,
1 on E of the original value, right? Alright. So that is that. How you finding C? How you finding C, the unknown capacitance? I know you all probably didn't really talk, but I think they give you R somewhere.
yeah,
Shucks. Did I
yeah.
prep out R? Yeah, I think I prep out R. Yeah, prep out R there. Right? But to find the unknown capacitance, we use an RC and then solve for C. I think I crop out R. Alright, take a little break. I don't know what year this was. I'm gonna look it up. Right, take a little break. We start back 7 o'clock. And we have 2 other questions to do a little bit harder. Take a little break. Alright, nice. Let's go again now.
So. Yeah, okay, now I can ask you.
Right, come on up. Let's start this one here.
Yes.
All right, this one here, well, I hope you guys got the graph. Right, so in 2021, they gave us something like this, right?
Yes.
Right? What you said, let's take a little read. This is 2021. The first part is just explaining how the electrons move and things, and charging and discharging, right? That's part A. Actually, you know what? I should make a try to re-explain this some. How that work? It is the way last week. I want somebody to try to explain.
So, but yeah,
When I close the circuit with the source and the uncharged capacitor, right?
um. Alright, so from. Alright,
You gotta be more specific, talk about the electron.
you have to go from. The.
From the negative terminal to the one on the plate, right?
Yeah.
No, what? No. When the electrons reach one of the plate, that plate becomes what? Negatively charged, right?
Yeah.
What does that do to the opposite plate? Why? Because it pushes the electrons away, right? And the electrons go away. To the positive. And now, since you have a polar, since you have two plates of different polarities, what's happening? Right, there's an electric field that builds up, which creates a potential difference. All right, now Right, take a read here. We're not gonna plot the graph, but we can get around not plotting, right? Take a little read there.
Micro.
Huh?
M. Right, micro.
M is mega.
Mega.
What's the shape of this graph? Without drawing it, what's the shape of the graph? But without actually plotting the graph is? Right, very good.
Ese que es lo más correcto.
Right, tomorrow people know all this, catch this now. Don't plot it, just catch the shape of it. So we can go on to the next part. You want to know it's a smooth curve, so my knee gradient and it's an abstraction. Right? Let's do a smooth curve there, Cristiano. Remember? To actually apply, you can plot it. Huh? No, that's cut, just do the shape. Okay, to do the graph paper. Somewhere after I got them. Hey, just do the shape of this thing now, there's some values.
There's like a left and a bottom left corner, so.
They actually get hard and dry.
What?
That's the going on, bottom left corner.
And a smooth curve, right? Right, just shape it out and let's go to the next part. Features and strength in the group.
Alright.
Okay, so I'm going to do. So, somebody is. So big, that's big, so, yeah, that's just that.
Right. Right, so you know what the shape looks like, right? Remember that discharging graph? Right, so the graph looks like this. What's the formula? What's the formula again for discharging? I is equal to what?
E minus.
Right, I naught e to the minus t on R.
Or C.
Alright. So you know what your graph looks like. Let's go to the next part now. The tan constant. Oh, by the way, write down what R was, please. Write down what R was because you might need it. But what does M mean again? 10 to the what? Capital M is what? M to the 10 to the 6, right? Nice. So let's see if we can figure out what they're talking about here. Take a little read. Right? So the question says that the time constant for the type of discharge curve obtained in part B may be defined as the time taken for the current indicator 1 on E of the initial value. Remember that? Time constant, 1 on E of the original value, right? What was the original value? And shall do a quick plot.
Yeah.
What was the original value? 17. So I know was 17 micro amperes, right? Nice. Use this definition and the graph to find the time constant. How are we doing that? Huh?
Linearize.
Nah, no linearizing. Using this graph. What you're going to do to find that t value? Jacob, help me with that one now, please. I know it's not business smartphone. When you finish it, I'll publish it. What I was asking is the question now. How are you going to get t from that graph? Yash. Huh? No, you can't learn it. They're using this graph. They're using a curve. They can do it. You want to find the time constant. How you getting that one from this graph? Yeah? Pick a point though. A point that you have to use when you have to randomly select. And you know I know, right? I know the 17. How you getting time constant? Plug in I know.
So you find T alpha. I know.
T at I know. T at I know is 0. So you get in there. Nope. Can't just do it, you gotta find a gradient. Anybody online want to try?
So this is but does have any use equal to 1 or 2?
Sort of. They told you there. So they want the time it takes to reach 1 on E of the original value, right? Can you find 1 on E of the original value? I don't know. I feel you meant to say 1 on E. Right? Because remember, time constant is 1 on E, right? Of the original value. So can we find 1 on E of 17? Come on, what is that? Average. Use the calculator. 17 divided by e to the minus 1. Sorry, e to the power of 1. 17 divided by e to the power of 1. 6.25. You're looking for e in the calculator, right by Lon. Huh? 6.25. Now, what you're gonna do with that 6.25? Come across and read off time. Okay. Right? And then you're gonna read up 2. That represents your time constant. Anybody? And your study graph, Yash? Right, just read off what is 6.25 now. Or you can access on the same after you use what is 6.25, what is time. 6.25 is equal to what?
18.
Right? So for this one, no linearizing, you can actually read it off. Right? It's like a what graph? Anybody recognize it? It's like a what? Half-life, very good. Half-life. Yeah, 6.25 on the Y, What's the x-axis value?
Five point nine eight.
Time 5.98. Right, nice.
Series crystal.
Remember those values in micro, huh?
Yeah.
Anyway, that don't matter, right? What do you get for time? Yash. What do you get for time?
5.98.
5.98. 5.98, right? Nice. Use the graph to find that. Next part. I need some help here from Cristiano. How we getting the unknown capacitance now? Which is C. I'm giving you a big help. I give you C. How we gonna get C, right? Very good. And then when you plug it in, where you going here? Where you plug it in simple, by the way? Which formula?
The C.
Well, let's see, that's it.
And which one is that? Yep. How to know? You know? Huh? Tell me now.
So I'm not,
Yeah.
so I'm not with that also.
Yeah. So you're using tau is equal to RC, right? Right? We know tau is 5.98 and we know that R is 1/10 to the 6. So C is what? You can do it in your head. C is what? 5.98 microfarads.
Yeah.
Okay? I need something electricity now, I will forget more.
No, I think it's
That's forget more.
Yes.
So,
Yeah, yes, I get more stuff. Yeah.
so it started with the good.
Yeah,
So let's finish this one.
I,
Calculate the charge on the capacitor when the switch is closed. Oh yeah, Paul, calculate the charge on the capacitor when the switch is closed. Sylvester, do this now. Hey, the last two parts some we done. Hurry up now. Sylvester, come now, boy.
I don't know. Like, that means, yeah, no, yeah.
Right? How we getting charged? Hey, you're getting mad.
so, you want epsilon and E to this.
No, but look at what you have. You want to find charge?
See that? Oh, no, we have three.
Yeah, charge.
Is it?
Yeah.
Charge is what? Charge is CV, nice. And we have C. Do we have we have B? We didn't get B is so yeah.
It's a lot. But Nana, you should have
Yeah, I know it's a son of some, I'm not playing it.
Right? How else we can do that one? I need some help. We know C. Yash, come on, let's figure out this now. And we done. The next part is a simple formula. How we getting this? We don't know V. So how we gonna get V? How are we going to get V? Right? We just say you can find current. And we know I, and we know I know it's 17. And we know the resistance is 1 mega ohm. So you can find V, right? So we can use V is equal to IR. 17, remember that's micro, right? 17 by 10 to the minus 6 by R, which is 1 by 10 to the 6. Now cancel and you'll get 17. Right? This will cancel and you'll get 17. And you finish, right? 5.98 by 10 to the minus 6 by 7. Everybody clear with that? So again, you identify a problem as V, you have to go back and see how you can find V, right? All right, and the last part, the summary formula we done, right? And we go into electricity here. I want to introduce electricity. Yeah. You using what? C equals to epsilon. E on E, very good. Right? And you know C, you know epsilon, and you know D. And then you find for E, right? All right. That's all in the pay attention. And then right in that. Let's go to electricity.
Yeah.
Right? You still have some more questions first to do that, but
So we're gonna do.
oh, the next piece here.
No.
Oh no. That's the passport. That is electric field. All right. So now you want to go to electricity, right? So any graph formulas. Oh wait, no. Are the wrong one? So when do we use the Lon method when they ask you to linearize? If you have a curve, you have to use what we just did. If they ask for a straight line or gradient, you have to linearize. All right. All right. So I want to introduce electricity, and we can start using this exact same table here. All right. What are the three most important quantities, Jacob, in electricity? What are the three most important quantities? Electricity, yeah. What are the three most important quantities that we need to understand? Right? Current, voltage, and resistance. Right? While we're here, could you help me with the formula for resistance?
R1 plus R2.
R is equal to, and here, 1 on R1 is. All right, nice. So you need to remember those small things, right? You remember the definition for voltage is what? Voltage is like how fast current actually electrons actually moving. Current is the number of what? Electrons per unit time. And resistance controls the amount of electrons, right? Okay. So you need to understand the difference between all of them. Something that's important that we need to also pay attention to is this. If I give you a circuit like this, when this switch is closed, right? If I put a voltmeter here, and I put a voltmeter here, would these two voltmeters read the same value? Okay, so let's say open. Let's say open, right? You're getting the voltage here. right?
That's EMF.
All right, and when it closes, you're not going to get the same value there, right? So what that means is that these two, somewhere in between, we're losing some volts, right? By the way, we need to remember electrical energy is what? Q by V, right?
Yeah.
Right? So somewhere here we're losing electrical energy. Somewhere here we're losing voltage. So something that you need to know is that inside these batteries, it have internal resistance, right? So some of the voltage is being lost. So this voltage that we measure here across the cell, we call that the EMF. And this voltage here, we call that the terminal PD, right? Some of the electrical energy here is being lost, right? So in definition now, how do we define, because they have the same units and everything, right? How do we define this? EMF is basically when you have other forms of energy giving you electrical energy. Terminal PD now is when you take electrical energy and you convert it to other forms. Okay? Because they both technically carry the same formula, right? They both carry V is equal to W and Q, right? But the difference is the energy change that happens in a cell is different to the energy change that happens in a load, right? Here, you have chemical energy giving you electrical, right? And here, you have electrical energy giving you some form, heat or something. Are you okay with that? So this value, as I said, this EMF value is not equal to this terminal PD when closed. We're using V for terminal PD. And the reason for that is across this cell here, there's something called internal resistance. So what you will see is instead of drawing it like this, sometimes they draw a cell like this. They have internal resistance and attraction. This here is welcome. Right? Right? And this here is your internal resistance, small r, is the external, big R. Right? So how can we create a relationship? How can we create a formula to kind of link all these things? Right? What we could say is energy supplied. We could use the conservation of energy. Energy supplied is equal to what? Energy used by the load plus energy lost at internal resistance, right? You should remember that energy is what? Energy is like Q by V.
Well,
In this case, it's Q by, let's call this E, right? Q by E. This would be what? This will be what? Coming up. Right? So remember, energy is equal to Q by V and V is equal to I by R. So can we write something like this? Can we write Q I by big R? Yeah? And here will be Q I by small r. And I can cancel these off, right? So I ended up now with EMF E being equal to EMF is equal to terminal PD plus I by R. Right? So this gives us now a nice relationship between EMF and terminal PD. All right? Everybody okay with that? So this is something new that we need to learn, the relationship between these two things. What would happen when the current is like almost zero? What would happen if I turn this on? Sorry, off. And the current in the circuit becomes zero? And by looking at this relationship here, what will happen? If I becomes zero, E is V. So your terminal PD now becomes the EMF. Right? The terminal PD becomes the EMF when the circuit is open. That's okay? So we need to understand it with it. Honestly, in notes, sir, but you can write it down now because you might never read that.
I did. Whatever.
Working on nice, it's 144. But it's have another question.
So you can do it like all the last year, but this one don't fit.
Huh?
You just control last year, but some this.
What's wrong?
The whole last year study guide, so.
Oh,
But it's not still fit.
yeah, no, so you guys, you know, then.
Right. And this is.
Hey, make sure the parents come for 8 o'clock, yeah, but I stand up outside.
Okay, that's it.
Yeah,
We asked me to see what. That's not possible.
but not one time.
If I stay until like a short week.
Yeah, you live outside in now. And that's man just pass around, happy tons and.
Yes, well, the problem.
Hmm?
Oh, no, I'm right, but
No.
I love that scene. Yeah, I guess well, in like national type of like competition. It's like chess.
Something, that's not more, a few things we done. You know, kids always had that kind of. Competing all that.
It's science that's represented.
Right, remember when you're doing things like this, you have to remember that little table on the top right hand there.
One.
Right, ready? Try this first one here. Right, Ansel.
Yeah, I'm not saying this.
Right, try this here. Ready? Try this now. A cell has an EMF of 12 volts. A cell has an EMF of 12 volts. An internal resistance of 0.5 ohms. A cell has an EMF of 12 volts and an internal resistance of 0.5 ohms. 12 volts. And an internal resistance of 0.5 ohms. 12 volts. An internal resistance of 0.5 ohms. if the current in the circuit is 4 amperes, if current in the circuit is 4 amperes, calculate the terminal P. Right, it's basic. Hurry up. Right, you're done. EMF is 12 volts. I just writing the values. Small r is 0.5 ohms, and current flowing is 4 amperes. Right, so to calculate V. So we could just use V is equal to E minus IR. So that's 12 minus 4. Well, you get 10. 10 volts?
Yeah.
All right, let's go again. The terminal PD across a battery is 10 volts. The terminal PD across a battery 10 volts when delivering a current of 2 amperes. The terminal PD across a battery 10 volts when delivering a current of 2 amperes. If the finish. If the EMF is 12 volts, calculate. If the EMF is 12 volts, calculate. If the EMF is 12 volts, calculate the internal resistance and calculate the internal resistance and the power loss inside battery. And the power loss inside the battery. Yeah, power loss, yeah. Let's do that and I have one more question and we're done. But this one is a theoretical one. I like this one. What they give you again? They gave you EMF.
Current,
They gave you, as you said, they gave you terminal PD, 10 volts. They gave you EMF, 12 volts. And they gave you current, you got nothing to do. And they gave you current, which is 2 amperes. So they get R already. Right? You should be able to get R. So you should have IR is equal to E minus B. I got IR to be 12 minus this, 2 volts.
Yeah.
So R is how much? 2 over 2. 1 ohm. Yeah, right. How do we find power loss?
That's not.
P is equal to what? I squared out. Very good. I squared out. Okay, that's how you find power loss. Right, and we know what I is. I is 2 and R is 1. So I got 4. Right. Last question is a little theoretical question. Think about it. Give my answer and be done.
That's not sense.
No calculations in this one. Tiny, what you answer for this one, right?
Huh?
It's not theoretical, fella. They punch you. I want the answer for this one, right? I'm gonna call it out now. Last question. Please write this one down and give my answer, right? Ready? Any questions on this one? This one's simple, right? We're just manipulating the formula, right? Right. Why is internal resistance undesirable? Why is internal resistance undesirable in car batteries? Why is internal resistance undesirable in car batteries, but less important in a small torchlight, like a torchlight battery, but less important in small torch batteries? As like them little double A, triple A kind of thing. Torch batteries. I mean, like batteries with torchlight. No, darling. Yeah. Think about it. Let's do it. Cristiano. What is it? Right. Well, am I here? What is it? Tomorrow double 2. That's 5. Take it. 5. 5.
Well, it's a t-shirt. Come on.
I got it. Take a group and sit down. Think about it and what you think. Why is okay? Why is okay in a torchlight battery, but it's not in a car battery? Yeah, Cristiano. Type it out here. You can do a little voice and let them listen to me and you get the answer. I know it's a chat GPT, man. Come here. Anybody want to try? Yeah.
This is my guess.
No, that's not a guess.
But
You get
no.
your food.
So ChatGPT said,
Yeah.
I'll tell you what ChatGPT said. ChatGPT said.
No, I want I want to
No,
try.
right, so I'll tell you what ChatGPT said, this is what I'm thinking. Each one, so.
That's not my hand. Okay.
I was thinking, you know, it's more about people that's in the part.
No, I
So the resistance, make a big difference.
Yeah, anything got you moved up. What about you? So,
I like that.
so,
Why I can't want that? A little heat could heat up the this.
what,
Yeah.
what is that one? Because they go on future. You call it. So, often, it just done. That's something, for,
Close, right?
Right, it's not.
Right. But right.
Whereas they're not happy, it's a it's something never. That's a league for trouble.
So you had to combine what he said and what you saying. Emily, what try again? Emily, what try again? Yeah.
Right?
All right. They get in there. All right. So you got to combine what you are saying.
The resistance and the big battery will have big difference. In the small battery, that's small difference again, but the small battery there was like that.
Right. So if you combine what everything all is saying, here's look at this here. Look at this here, right? So your battery have an EMF. And as you said, cars require a large current. Okay? If you have a large current and you have internal resistance, it leaves the voltage, the terminal PD available small. And then it wouldn't be able to start the car properly, right? Right? But in a battery, this high value needed real small. So even if you have internal resistance, it's not going to affect the terminal PDI you're getting. It's not going to affect what you're getting when it goes to circuit. So that's okay if you have internal resistance for a small battery. That's okay? Right? So in a small battery, you would this V value, right? This V value wouldn't be affected much. But in a large battery like a car, it'll be affected a lot. So you want this internal to be as small as possible. Okay? All right. So that's the intro to this. Remember all of this because we're still good on. Oh, you gotta prove this as well, right?
Yeah.
Just I like that. I really like that. Really like that. A step in the right direction, man.